change in the program. And I'm very, very pleased to introduce Andrew Taylor in his second talk, Consistent Theories and Consistent Logics. Please, Andrew.
Thank you. And thanks to the organizers again this time for allowing me to speak once more. And for everyone else, I'm very sorry. This will be over reasonably quickly, I promise. I can't promise it'll be painless, but I should say this is joint work with Ruhr-Universität, and she's a PhD student at the Ruhr-Universität Bochum, from where I'm coming, and we both became aware of some work going on in a project that Heinrich Fonsing is currently running on the topic of inconsistent logics, and well, we just found it a fascinating topic and wanted to do something in the neighborhood, so this is the topic. So I'm going to start by saying a little bit about what I mean by the phrase inconsistent logics. I'll tell you a little bit about them and distinguish a couple of different ways of talking about logics, and talk about two different ways of talking about theory. And the goal basically is to try to consider the question whether you can have a logic which is inconsistent, as a little spoiler in the sense of having contradictory pairs of theorems, but which still allows you to have deductively closed sets of sentences which are consistent. Now, according to one notion of theory, I'll say that it can happen, but according to another notion of theory that I'll discuss, it in fact can, and the point of the talk is to give a bunch of examples of when this sort of thing can happen. The example that I'll start with, and the one that places this talk somewhere in the vicinity of the subject matter of the workshop, are relevant CONNEXIVE logics. So I'll give some examples of these things and how you can build consistent theories in them. Then I'll give a very general result that we managed to work out, building on how you build consistent theories in this setting, to allowing us to give a general characterization of some properties a logic can have, which are sufficient for allowing for consistent theories. And then I'll talk about I'll be talking in the first bit very abstractly about theories, and in the last section I'll introduce some actual concrete mathematical theories, very, very tiny mathematical theories, but with a bit more going on than just abstract nonsense. So, and then I'll talk about mathematical theories in Abelian logic and how we can give some consistent theories in this inconsistent logic. Right, so as I already spoiled, by inconsistent logic, I'm going to need a logic, including at least a unary connective, such that both A and not A are valid in L for some formula A. Now, I'm being a little bit cagey about what L is. Might be a set of theorems, it might be a constant relation. In fact, in general, I'm going to be thinking in terms of a constant relation, but a lot of what I'll have to say later would also work if we thought about a logic as a set of formulas. And inconsistent logics then are just logics that are inconsistent as sets of theorems. Note, this is a very different use of the phrase inconsistent logic than is common in algebraic logic, where the inconsistent logic over a language is just the trivial consequence relation over that language. I just say that so that you don't think I mean something other than what I mean, which is the thing I set up here. And as I mentioned, Heinrich has given in a forthcoming paper a very broad survey of well-motivated inconsistent logics that have shown up in the literature, including some variations on CONNEXIVE logic. And as I mentioned, this project sort of built up from Heinrich's work. Okay, so just by way of a little bit of motivation and sort of preliminary discussion, the move from paraconsistent logics to inconsistent logics seems to be kind of a substantial move, right? A paraconsistentist, by my lights, only has to allow that there are some theories closed into the logic that are inconsistent but non-trivial, right? Whereas endorsing an inconsistent logic does more. So a paraconsistentist has the range to still be a non-dialethiist in a sense, that they can admit that while there are inconsistent and non-trivial theories, they can still say that none of those are correct as theories. And many paraconsistent logicians have said something like this. Maybe these theories are interesting for some other reason, but we're not actually endorsing. But once you endorse an inconsistent logic, then you have to think of at least one theory as inconsistent and correct, namely the correct theory of logic. So endorsing an inconsistent logic takes you a step further beyond paraconsistency by seemingly embroiling you in some form of dialetheism, at least as far as the word correct goes. Maybe you don't want to tie it to proof, but at least in terms of sentences you're going to endorse, you're going to have to endorse something of the form A and not A. So inconsistent logics really are a big step beyond paraconsistent ones. And indeed, on the standard Tarskian notion of theory, where we've got, let's have another pause in here. We've got that a formula is a theorem if only if it follows from every set of premises. Then for any theory, by which I define that to mean the standard thing, a set of sentences that is closed under all consequences that we get from the set of sentences, we have that the logic understood as a set of theorems belongs to every theory. And so not only that, but if you take the Tarskian notion of theory, the person who endorses an inconsistent logic has to say that every theory, correct or otherwise, is inconsistent. So it seems like it gets you rather a lot right away. But that result, this one, relies on taking this notion of theory, particularly relying on distinctive features of the Tarskian consequent relation, right? Which is a monotone, transitive, reflexive, structural relation between sets of formulas and formulas. And if we do something that allows us to adopt some kind of non-monotone consequence relation, particularly non-monotone in the sense that we can't uniformly step from requiring that if A is a consequence of the empty set of premises, then A is the consequence of any set of premises, then it may well be that we can have theorems which are not entailed by any premise set, right? This is basically one of the key moves in relevant logic, which I'll talk about in a moment. And so one way to talk about such a non-monotone consequence relation in this particular sense is to think about the internal consequence relations of relevant logics, such as say R, where we've got an implication and a conjunction, and we'll say that a premise set entails internally a formula, just in case either there's some finite subcollection whose conjunction entails A as a theorem of R, or that premise set is empty and A is already a theorem, right? So this way we block this particular move. And we can have formulas which are theorems but aren't entailed by any premise set whatsoever, but are only entailed by maybe the empty set or themselves, something like that. Okay. And here we will indeed have theorems such that there are formulas where A tells you that A doesn't entail R tells you that A doesn't entail B. If, for instance, we pick any particular theorem and a formula that doesn't share an atomic formula with it. And if we adopt a notion of theory that answers to something like this consequence relation rather than the Tarskian one, then we can, it seems, have inconsistent logics with consistent theories because we're not going to force every theorem of the logic into every theory. So then the trick is just to find ways to keeping out the theorems of the logic or not requiring them to be in, still keeping everything nice and consistent. Right, so the trick I'm going to use here builds on the notion of L theory defined by Richard Silvan and Bob Meyer, which is used in the canonical model completeness proofs for ternary relations, semantics, and relevant logics. And this is basically just a filter in the Lindenbaum-Tarski algebra. Or put in a slightly different, maybe slightly nicer way, I'll say that T is an L theory just in case that it contains any formula such that there is a finite set of formulas in the theory whose conjunction provably implies that formula. I'm going to talk here about consequence relations defined basically like this, but we can get around this so we don't have to require logic to have implication or conjunction if we adopt an appropriate sort of non-monotone consequence relation, and then we can use something like the usual definition. The notion of a non-monotone consequence relation I have in mind here is not the sort of Mackinson style, the sort of defeasible style, but rather something more akin to work that's been done by Arnaud on simple consequence relations and variations on that. So I'm going to talk in a way that uses this language, but you don't, strictly speaking, need to include this. You can get around it somehow. Right, so if we do this, we can have theorems that are not provably implied by every formula. And so we can construct L theories that don't contain the theorems of the logic. In the parlance of relevant logic, these are called non-regular theories. A regular theory is one that contains every theorem, and a non-regular theory is not regular, but still a theory. Okay. Right. The distinction between these two kinds of theories actually does have some philosophical bite to it, and it's been built into a certain philosophical acts that relevant logicians and their fellow travelers have been grinding for a few decades now, famously by Bob Meyer, but also more recently by J.C. Beale and Shay Logan and some others, where we distinguish between seeing logics as collection of facts and logics as collection of laws, right? Seeing logic as a collection of facts requires you to understand logics in terms of theorems or true statements, whereas seeing them as collections of laws rather sees them as telling you how to reason or how to engage in a deductive closure or that sort of thing. You see them not as a collection of logical truths, but as followed from facts, right? And this way of seeing logics relies on understanding them as theories of entailment. Then logic is, to put it the way that J.C. Beale and Shay Logan have, logic is an engine for generating the deductive closures theories. Or to put it in Shay's particular terminology, it's a universal theory of theory closure. And then on such an account, the presence of non-regular theories indicates the way in which a theory might be closed under logic without being itself about logic in any significant sense. You can use logic as a tool to generate the consequences of the premises given to you by your theory, but that theory needn't say anything about logic. It needn't tell you all the theorems, it needn't tell you any theorem. It just, tells you what to draw, what conclusions to draw from your premises. And as I mentioned, making this distinction does require enforcing some relevant stuff, particularly enforcing that this form of monotonicity doesn't hold. That not every premise set entails every theorem. Hence, the class of logics, which I'll be talking about, are going to be relevant in some sense, although not all of them will be relevant in the variable sharing sense, because, for instance, Abelian logic, which I'll mention at the end, is not relevant in the variable sharing sense. Okay, so crash course in relevant logic, or in this case, B. Here's an axiomatization of B, which is the basic logic of ternary relation semantics. It's axiomatized in terms of axioms and rules of proof. Rules of proof, by rules of proof, I mean rules that tell you that if both the premises are theorems, then the conclusion is also a theorem. So not rules of inference, to use the distinction made by Smiley and I think made famous by Humberstone. So we've got rules of proof for most ponens, combining theorems into conjunctions, sticking arrows together in a transitivity sort of way in contraposition. And then as far as axioms go, what we have is basically that these things are lattice operators that are distributive, and the combination of these negation principles tell you that negation is a De Morgan negation, appropriately enough. So here's B, and we can obtain further extensions by adding extra axioms and rules. The main system I'll talk about is going to be an extension of which we can get by adding the following axioms and rule. If you know about E, then you can look at these. If not, it doesn't really matter because the facts I'm going to tell you, well, you can take my word for them. And then to obtain R, we just add an axiom form of this rule, which is a form of permutation. Okay. There are some axioms for some relevant logics. And given any of the relevant logics considered, we can get a connexive extension, which given a logic L, I'll call L, following Chris Mortensen, by adding our best friends by now, the Aristotle and Boethius theses. And in any such extension, we're going to get some inconsistent theorems. And particularly because in B, we can prove that any contradiction entails its own negation, which will, of course, contradict the salient instance of Aristotle, as we've talked about in many different guises. And in fact, following a result due to Meyer, this means that if we add the connexive principles to R, we get a trivial system. Meyer basically proved that any inconsistent extension of R, which is closed under substitutions, generates the trivial logic. So R is a non-starter. But Mortensen, in a paper in 1984, showed that if we add the CONNEXIVE principle to E, we get a non-trivial logic, and so hence all of its subsystems, including, for instance, VA, are trivial, but inconsistent. Right, how do we get the non-triviality result? Well, we've seen lots of matrices, and here's another one. We use a three-valued matrix, 0, 1, and 2, with 1 and 2 being designated. These, hopefully, these familiar operators, where we take 0, 1, and 2 to be ordered in a usual linear way, with and an or as the min and max with respect to that linear order. And then this sort of LP-ish negation and this implication, which is kind of goofy. Now note, given this, we can show that that EA is non-trivial because if we take the instance of the thing that Aristotle's thesis negates, where we plug in 2, or the other version where we plug in 0, we'll get something that is non-designated, and so EA won't prove either of the things that Aristotle's theses negate. And it's a long, tedious proof to check that this matrix is in fact a model of EA, or you can make software do it. If you do that, I recommend you use John Slaney's Magic matrix generator for implicational calculus, which is a lovely piece of software that everyone ought to play with because it's so much fun. Now, we can use the soundness of EA with respect to this matrix to show how to build some consistent EA theories. And so in particular, how to build consistent L theories for any sublogic of EA. One thing to remember when I go to the next slide, which has, I think, a proof, is that these things, if you plug in the classical values, you get the classical value. Same thing with negation, not so for implication. Right, so given a set of formulas, we'll describe the theory, the L theory generated by that set of formulas like this. Basically, it's a set of anything that you can prove from formulas in your set of formulas. Then, if P is an atomic formula, then the principal theory generated by P is going to be consistent. What's the proof? Well, if that weren't the case, we'd be able to prove that P entails A and not A for some A. But on any interpretation in Mortensen's matrix, any contradiction will either take the value 0 or 1. And so we can just fix an interpretation where P takes the value 2, and then we'll get an implication for value 0. So we can always falsify formulas like that. So this thing will always be consistent. And in fact, we can go further and say that if a set of formulas doesn't include any occurrence of the arrow and has a classical model, then the theory generated by that set of formulas will also be consistent. So if you don't talk about implication and you only say things that are classically consistent, then EA isn't going to force you to put any contradiction in. And here's the basic argument. Suppose P is not just in X, but an atomic subformula of any formula in X, and it takes the value T in the classical model we've assumed exists, then assign it 2. If it takes F, assign it 0. And then any formula in X is going to take the value 2 just in virtue of the fact that this has a classical model. And then once again, we can show that there isn't any formula of the form A and not A, which is provable from formulas in X using the same matrix counter model. So EA is inconsistent, but it doesn't force you to be inconsistent unless you are already, or you talk about implication. And in fact, talking about implication is enough to make you inconsistent for kind of a goofy reason. Well, that's not quite right, but there's something right in the vicinity of what I just said. So any consistent classical theory, which no mention of that, will generate a consistent theory. And the reason basically is that EA, like E, has the so-called Ackermann property, which is that no formula that's not itself an implication formula will entail any implication formulas according to EA. So you only get implications if you put in implications. Note, this is not the case for negated conditionals. Negated conditionals are very easy to put into EA theories because these are theorems. So if you put in any formula, you'll get that negated implication concerning that formula. And if you put in that formula, you'll get that formula. And basically the reason for this is that we have a form of the counterexample axiom provable in EA. Actually, I should put my cards on the table. EA is kind of a silly logic because it proves every negated implication formula. However, this property and this property don't hold for sublogics of EA. So if you go down to weaker and, for my money, better relevant logics, then these things aren't an issue. So EA is kind of silly, but it's nice because it has nice sublogics, and the kinds of properties I'm concerned with transfer down from logics to their sublogics. Okay, so that's the sort of concrete method. Let me look now at how we can generalize that to get a stronger result. We can take the sort of structure and provide a general criterion which holds for a number of known inconsistent logics, so we can show that they also will admit consistent L theories. Well, let me put another card on the table. There's a very boring way to build a consistent theory, a consistent L theory in almost any logic, and that's to take the empty set, which is always going to be an L theory. But ignore that, we can build slightly more substantial consistent theories using a general construction. So, what we needed to do in order to make the consistent theory result work in EA was to be able to sort of cordon off designated values that true contradictions take, and have at least one other designated values where implications from this one to the contradictory value are non-designated. So this is part and parcel of not having every theorem be entailed by every formula, is that we can move from designated to designated values and get a non-designated value. And in fact, we can use this trick to generalize. So here's a big theorem. Okay, suppose we have a logic which contains at least an implication and a negation. You can also throw in a conjunction, and if you really want, you can do away with some of these language restrictions by working with non-monotone consequence relations. But let me just talk about connectives to keep things simple. Let X be a set of formulas in this language. Suppose we have a matrix where we have disjoint subsets of the collection of designated values, such that L is sound with respect to the matrix. So the matrix is a model of L. And for every X in the model, if both it and its negation take a designated value, at least one of those is going to take a designated value in C, this special contradictory collection of designated values. We require D prime to be non-empty and closed under all the interpretations, all the operations interpreting connectives and occurring in X. That's just the technical requirement. And we require that X arrow Y is not designated if X lives in D prime and Y lives in C. So we cordon off the contradictory values and allow implications to not be satisfied if they go from some of the nice designated values to some of the contradictory designated values. Oh, and you should preserve modus ponens because modus ponens is nice. If you do that, then the theory generated by X is going to be consistent. And I kind of walked through the proof in stating the theorem, but let me say a little more. Point 2 guarantees that if we've got a pair of Y and not Y, which both are designated, at least one's in C. So if we assign each atomic subformula in X a value in D prime, then each formula in X is going to take a value in D prime. So, but that tells you that if X is the value of any formula in big X under this assignment, and Y is whichever of these two, Y prime is whichever of these two values lives in C, then X arrow Y prime is not going to be designated. That takes care of the case where both Y and not Y are designated. But if Y prime is one of these values and it's not designated, then the modus ponens thing tells you that the implication will not be designated. Given all this, we want to show that no contradictory pair of formulas are going to appear in the theory generated by X. But it follows that at least one of a pair of A arrow B and A arrow not B, oh, this is familiar territory, for any A occurring in X or conjunction of those, and formula B, one of these two is going to be undesignated in our matrix. So by point 1, which is that L is sound with respect to the matrix, we know that one of B and not B will not appear in this. That's for any formula B. So this will be a consistent theory. Right. We can do away with one of the assumptions by complicating things a little bit. But I'm not going to talk about that because it's just showing that the result is slightly more general, but you got the basic picture, right? Right. And there are lots of inconsistent logics which we can show to have consistent theories using this general result. In particular, we can show it for any logic which has a classical fragment in the language of the sort of Boolean triple, and a conditional which is, for instance, sound with respect to the Mortensen matrix that I showed you earlier. That's obvious. But it has some nice examples. For instance, every sublogic of the inconsistent logic Cn, if we take implication to be the strong implication. If you don't know strong implication, there are two implications in Cn. One is bad and irrelevant, and one is nice and relevant-ish, and you pick the nice one. And C is one such logic. So we can build consistent theories of C so long as we take implication to be the strong implication. Next, we can do it for any logic which has a classical fragment here and a conditional which satisfies the R, or which is sound with respect to the Rm3 conditional matrix. I won't walk through the reason why, but we can talk about it later if you like. But there are lots of logics that satisfy the Rm3 matrix. I think it shows up quite a lot. And furthermore, with this sound with respect to any matrix where we have this form, where we can split up 1 and 2 and have implications from 2 to 1 be non-designated. Great. So far, okay. So that's the general result. And it goes to show just that even if we ignore the sort of boring case of consistent theories, we can build consistent theories out of, for instance, classically consistent theories in a range of inconsistent logics. Basically, so long as the logics don't force your L theories to be regular, we can pull the regular and inconsistent theories apart from the non-regular consistent ones. There will also be some non-regular inconsistent theories, but not very. Let's talk with a little more substance or a little more concreteness now. We can build theories that are slightly more substantial and involve a bit of mathematical context if we, for instance, work in the logic Abelian logic developed by, among others, Meyer and Slaney. We picked A basically because it has a very, very nice, easy semantics. So this logic can be axiomatized by some axioms I'll show you in a moment. The thing to note is that we take negation to be defined in terms of an intentional falsity constant, where we basically don't require anything to hold of that, just that it's a propositional atom and we define negation in terms of it. Then if we add the following axioms, we get an axiomatization of A. This is maybe not an especially enlightening collection of axioms, but the one thing to note is that we generalize the double negation elimination axiom so that it holds for any formula in the place of where the falsity constant would usually go. Now, axiomatically is not the nice way to see this logic. The nice way is semantics. And its semantics is incredibly simple and nice. It is, in fact, complete with respect to, ignore that word for now, lattice-ordered abelian groups, where a lattice-ordered abelian group is an abelian group, where this is the group operator, and that's the inverse thing, and that's the identity, where this thing is required to be commutative. And we've got a, again, ignore that word, lattice reduct with the lattice operators, where we can, if we want, just define conjunction meet in terms of joint, and the group operator has to distribute over the lattice. This is a very simple semantics. And in particular, one of the nice things about abelian groups is that you actually don't need to pay attention to all abelian groups like this. You can just pay attention to the integers, ordered by addition minus and then these things just as min and max. And in fact, Abelian logic is complete with respect to the integers with this lattice structure on top of it. So in Abelian logic, one of the reasons it's so beautiful is that you can just recall doing some like middle school algebra over the integers and prove all sorts of things about Abelian logic, which is fun. And furthermore, this provides a semantics for a quantified extension of A, where we also add identity, if we now stop ignoring this word complete.
Sorry, 10 minutes.
10 minutes, okay. I'm almost done. Yeah, I'm almost done. We can provide semantics for a quantified extension where we add the following usual sort of axioms for identity, sort of a Leibniz's law thing and another Leibniz's law thing, stated for terms and formulas respectively, or anti-respectively. In addition to some more or less standard looking axioms for the universal quantifier, and then a defined existential quantifier. All right. And I should say, given an interpretation of the language onto these structures, we'll take a formula to be satisfied just in case its value is above 0, which in the general case is the unit of the group operator, but in the case of integers is 0. So if it has a positive value, it's satisfied. One other thing to note in the integers, the only element whose negation is above 0 is 0 itself, right? So minus 0 is 0. And any positive thing will have a negation, which is a negative value. So basically the trick we're going to use to build consistent theories is just to make sure we stack the axioms of the theory in strictly positive values and require the rules to generate strictly positive values from strictly positive values. So we know that A is an inconsistent logic. It proves both AROA and not AROA. Basically because any formula of that form is going to take 0 as its value. And so that thing's 0, so that thing's 0. So in any model, you'll have both satisfied. So A is not just inconsistent, it's real inconsistent. In fact, just to say, inconsistency comes extremely cheap. If you've got a theory, an A theory, that contains any self-implication, then it's going to be inconsistent. Furthermore, if it contains any biconditional, then it's going to be inconsistent. And that basically is for taking 0 reasons that I'm not going to go into. But we still have room to maneuver, and we can, if we're careful, still shove the values of axioms of a theory into the positive values. So here's a theorem. If we've got a theory of this quantified extension of Abelian logic, and T has a linear model, that is where the carrier set of our lattice ordered group is linearly ordered, like the integers are, where all the axioms take a positive value, then T is consistent. That's the point I've just made already. And here's the argument for why, but I think I've already talked through this argument essentially. It's just that if you force all the axioms to take a positive value, then any provable implication from some axioms to some other formula will require that other formula also to take a positive value. So anything you can derive from things that take positive values will also take positive values. And so long as you start with positive stuff, you'll stay with positive stuff, and you won't have to throw in any contradiction. So, for instance, we can generate a similar result to the kind we showed for relevant and connexive logics. If X is an implication-free, classically consistent set of formulas, then its theory under quantified Abelian logic will also be consistent. I'm going to talk through the proof, but it's sort of similar to what we've seen already. Let me talk about two very, very simple mathematical theories that will show to be consistent, which will generally show you how to do this sort of thing. Right. We need to ensure the mathematical axioms are positive and the axioms have a classical model. Here's a way to do it. Let the theory be that theory in the language of R, binary R, of equivalence relations. So it's got to be reflexive, transitive, symmetric. These things we throw in basically to ensure that contradictions don't show up. If we do that, then the theory generated by these axioms will be consistent, and we can build a model out of the natural numbers and the integers by taking the value of any self-implication and any negated self-identity and any negated identity for actually distinct natural numbers to be 1. And we'll take our A, B to be 2 for every A and B. So I should say N are the things that the terms range over, and Z are the values that they can take. Then, I'm not going to walk through the argument, but all of these axioms will take a positive value, and you have to just do some computation. You can verify that. I can send you the paper, and you can see it written out in full glory if you like. So, at least the theory of equivalence relations, if you state it in this classically redundant way, will be consistent in Abelian logic. We can do the same thing with the theory of successors. So, this is a relational theory. Here's a functional one, just because, we've got to cover our bases, right? So we have a language where we can name 0 and take successor, and we define some successor axioms. So 0 is the successor of anything, successor is objective, and if something isn't 0, it's the successor of something. These are familiar axioms. And we can prove that this theory is also consistent by using a model. And for some reason, I decided to show you the gruesome details here. But given the time constraints, I won't walk through this, just to say we can, in fact, construct an interpretation which forces all of these axioms to have positive values. And once again, we're done. Right, so if we adopt this internal consequence relation and the salient notion of theory, the L theory, then it's perfectly possible, and in fact, relatively routine to construct consistent theories even for inconsistent logics. And we've shown a number of methods for how to do that. Yeah, including even quantified logics with some non-trivial, well, for some value of non-trivial mathematical content. The upshot is that even if the logic itself is inconsistent, that inconsistency needn't spread to all deductive reasoning that the logic supports, so long as you understand deductive reasoning in the right way. And if you have relevance intuitions like me, then you should want deductive reasoning to mean that in the first place. So, if you don't have relevance intuitions, here's a reason to have them. And it also makes good sense if you take on board this account of logic as a body of laws rather than as a body of facts. So what it matters is not what logic says is true, but rather how logic tells you to deductively reason. Some natural steps here are to use these tools to investigate a wider range of inconsistent logic. We've just picked a few that we know well and are easy to use, but Heinrich gives a number of examples in the paper, I think almost none of which we've talked about. Maybe we mentioned C and CN. You do mention the Abelian logic, okay. Well, there are lots of other logics that he mentions, and it would be interesting to see how the methods apply there as well. Also, it'd be nice to say more concrete things about the structure of inconsistent theories in these logics. So I've only showed you a handful of very simple facts about L theories in relevant connexive logic, but it'd be nice if we look at some of the weaker ones, which don't validate every negated implication and where not every formula entails a negated implication, to look at theories with implication in some of that setting and see what happens. I think that'd be neat. But I'm going to do that later, because right now I'm going to thank you for listening to me once again and show you some references.
Thank you, Andrew. Thank you. Kind of the questions? First,
well, it's a comment and question. Thank you for this very interesting talk, which shows me that it's very important for each of us here to try further to clarify the differences and maybe common features both of connexive logic, of relevant logic, and consistent logic. So it's helped me quite a lot today. your focus was mainly on inconsistent logics today, but in between you had a chapter where you were dealing with relevant connexive logic. And did I get you right that the system B, which details of which I didn't know before, can be extended to a relevant, to a connective system, which is consistent?
Yes.
Okay.
Yeah. And can stronger subsystems up to, but not including R.
Okay.
So there's a wide range of relevant connexive logics there.
Okay. Then I would be interested, where does it come from, so to speak? You just showed us the actions characterizing system B, which are all, of course, classical theorems. So instead of having the list of actions, it would be interesting to have a list of what does not hold in system B in comparison to. Can you just briefly explain it?
Well, some of the most salient things that don't hold in B are some of the axioms I showed you right after, like these ones. So for instance, we don't have a nested transitivity. Sometimes this one has been likened to the syllogism in Barbara, or by Australians, so with an Australian accent, the syllogism in Barbara. So we don't have either of these principles. We only have more restricted forms of transitivity, so that if that's a theorem and that's a theorem, then that's a theorem. We don't have the rules or axiom form, I should say, of contraposition.
You don't have the full. Okay.
No, we have a rule form, so that if this is a theorem, then that's a theorem. But in B, you don't have the form where you can freely substitute in for A and B. We don't have this thing which looks like modus ponens, but is actually just contraction in disguise. So you can't just contract multiple occurrences of the same antecedent, and neither can you permute occurrences of antecedents. So B is really a very weak logic. Basically, what it allows you to prove are things about distributive lattices with De Morgan or FDE style negation. And for implications, you can prove self-identities and you can chain implications together, but that's basically all you can do. So B is really a very weak logic. But I should say that we can get non-trivial connexive logics from these, even if we add all of these axioms and this rule. So B is really very weak. R, if we add all of this stuff, is too strong, because if you add the connective principles, it explodes. This becomes the trivial logic, or the inconsistent logic, the way algebraic logicians use the term. But if we add all of these things, we can still have a consistent system. And in fact, I suspect that if we add just these four, we can also have a consistent connexive or relevant connexive logic, which doesn't have the sort of funny end of EA, which is that we can prove every implication. I haven't verified that if we just drop this rule, we get that, but I suspect it's true. And if someone happens to have a copy of Magic running on their computer, it's something we could check before doing a new one. I don't know if that addressed what you were curious about. But, yeah. Right.
Anyone else?
Okay, so you emphasized the great talk. I really like this one. You emphasized the distinction between logic as a collection of facts and logic as a collection of laws. So what would you say if someone says, yeah, well, I endorse non-trivial negation because it's the logic. And when I do not only want to apply this logic in my reasoning, I will also commit myself to the theories.
Sure.
What do you say? You say, okay, then you should, of course, then be ready to live with every regular theory, the relational inconsistent. Or would you say, no, this is bad?
Let's say the former. I mean, look, I'm not going to tell you what theories you ought to construct. I think there are probably good reasons to, well, I don't know about allow there to be consistent theories. I mean, I'm not sure what stance to take on that. I suspect a lot of people are going to want there to be consistent theories, and so they'll have a reason not to endorse the position you've mentioned. Although, then again, if they want to be consistent, they're probably not going to be swimming around with inconsistent logics in the first place. But this funny hypothetical person, if they endorsed inconsistent logic, but still wanted to be able to reason consistently in some cases, would have a motivation for allowing some non-regular theories. And so I also think you can endorse the laws of logic qua facts rather than laws, or in addition to laws, while at the same time understanding theories in a way that you don't require all of them to include all the theorems. If, for instance, you take a theory to be generated by a hypothetical contra-class or contra-factual or contra-logical perspective, then I think you can absolutely endorse the principles of logic as facts while still having room for admitting the kinds of theories I've been discussing here. But yeah, I mean, I'm not here to be the arbiter of what theories you ought to build. I think the interesting thought here is that even if you have an inconsistent logic, there's a way to be slippery and not have it generate inconsistency in every theory. And I think that's an interesting fact that gives us more flexibility, even for people who otherwise might be suspicious about endorsing an inconsistent logic.
Right. Professor Luis?
Sorry. Yeah, it's a question about the organization and presentation. It was curious how you started with Mortensen's the CONNEXIVE version of E instead of CN, for example, since they are basically the same one.
I'm a relevant logician by trade.
Yeah.
And I like the tools I know best.
That's the answer.
It's not a very exciting answer, but that is the answer.
That's
It's everywhere, so it's at least got that going for it.
It was because it makes easy the connection later with B and Bochum.
That's
You start with B, then you start saying things about R, and then Abelian logics. Here's more or less
that's not the kind of picture I had in mind. Basically, okay, so the way this paper sort of grew up is that I thought a bit about relevant connexive logics and went, there's a paper here, and talked to my co-author and said, I think there's an idea here. And she went, yeah, here's some things we might try to prove. And then we stuck our heads together for a while and proved some things. And so the focusing on relevant connexive logic is really just a sociological, or not sociological, psychological result of psychological facts about me. For Abelian logic, the reason was extremely utilitarian. It's that this semantics is incredibly easy to prove things about. And it's very easy to see, for the reasons that I mentioned a few times, that if we can build models where we keep all the values positive, then we get a model that has a consistent theory as its set of satisfied formulas. So we landed on Abelian logic basically because the semantics is so simple, and you can, like I said, just do some like middle school algebra to prove things about the logic, which is, I think, also the reason why Meijer and Slaney introduced it. So I didn't have any idea in mind about like the relation between Abelian logic and the quantifying relevant logics. It was just, we're smelling around for inconsistent logics that have a simple enough semantic presentation that we can come up with a nice characterization for consistency in that setting. And Abelian logic fit the bill. There's nothing deeper going on in terms of the presentation. I hope that's not too disappointing.
a little bit.
Sorry. And please everyone.
Yeah.
Anyone else?
Yeah, speaking of psychological stories and states, so on, it's say very strong things about CONNEXIVE. This is my part.
Which the CONNEXIVE?
Yeah. I like that logic very much, and you say that it's
I agree. What do you think about Abelian logic? It is because of the semantics that you can make sense more easily of the strange theorems in that case. So we develop semantics for CONNEXIVE or happy. My question is it about the semantics or the logic?
It's just about this theorem. Like proving every negated implication seems very odd. And I should say, in relevant logic, generally speaking, negated implications are funny. If you go weak enough down to systems like B, you don't prove any theorems of this form. Whereas if you go to EA, you prove all of them. And somewhere in between, you get other systems where you prove theorems of this form only if and only if that A is a theorem and the negation of B is a theorem. So you get really odd behavior for negated implications. So, I mean, yes, you're right, I was using provocative language to describe EA. But the things that I find odd about EA are, to be fair, odd about, or variations of the thing that's odd about EA are odd about a bunch of relevant objects. Basically, negated implications, we just don't know what to do with them. We can't do the sort of simple classical thing of requiring this to be equivalent to A and not B, because that's just irrelevance waiting to happen. And if we have too much of it, then we wind up with other unpleasant results. So the question is, what does a negated implication mean? And I don't know the answer to that. And EA seems to me to overgenerate. B undergenerates. And I don't know what the golden mean sort of path is.
C,
Maybe. Anyway, that's, yes, I was being polemical and all that, but
I like that result actually. All conditionals are old. I grant you, you need a very strange picture about the nature of conditionals to make sense of all of them are false. I always say that I like that.
I would be extremely curious to hear what that number is. So I would love to talk about that. Let's do it.
Okay. Just like I'm curiosity, I'm really ignorant about connectivity, honestly. It's the
It's good work up for you to come.
yeah.
It came up a lot.
So I wonder if there's sort of similar approach like this formal logics and formal consistency for the like syntactic way to approach all these phenomena. Is there something like that, or it's not? The approach cannot work here.
Sorry, so some form of like using these results for logics of formal or
No. Like when you get some results, I mean, work of a price to pay question because I was wondering if there's some connection between this logic of formal consistency and the way it is the approach is syntactic, right? I mean, you can have funny semantics for that logics, no? But in this case, connectivity cannot be approached via that, let's say, labeling of these formulas are consistent and other are not. I mean, probably it doesn't even make sense.
I don't know, and it's not something I've thought about. I have to confess I'm blamefully ignorant of logics of formal inconsistency. So I'm afraid I don't have anything helpful to say, but if you have thoughts, I'd be curious to hear. But those are logics which I'm aware of their existence, and that's about all I know. So
I mean, they are not called classical. They are power consistence. It's a good one.
Please. And just we comment on that because it has worked that something. It has this calculate version of the and it includes split with the bullet. Okay. There is some work in that, but not exactly one.
the full family of advice. There is at least that one. What's the name? Well, you have to, yeah, I mean.
A quick comment on the ugly beer and the left. Louis and I have a paper with Morton in Logics, kind of discuss some ideas on how to explain very briefly and how to explain these kind of things. We were thinking about something similar to antonyms. Maybe you remember Richard Silvan talking about antonymatic implication, in the sense that one can never have whatever is sufficient for something to be implied out of some information. And the other thing I wanted to point out is I have been writing about the logics which are relevant in CONNEXIVE, and I found out that there are some conditionals, for instance, missing branches or alcoholicos conditional, that will give you these theorems as well. Every negated conditional is theorem, but you won't have logical relevance. So this kind of result is not limited to the relevant realm, but it seems to be that three-valued three matrices for CONNEXIVE conditionals may sometimes give this result, especially with power consistent negation like the Morgan or setless negation.
Perhaps you could send me that out. We'll be very happy.
Yeah.
Thank you.
No, thank you.
There is no more time. Thank you for being here today. Thank you.